Welcome to our comprehensive guide on data management and reproducible workflows in Stata, specifically focusing on versions 18 and 19. This presentation will walk you through the entire process, from initial data ingestion all the way to robust analysis. As highlighted in the quote from Advanced Architectural Frameworks for Data Management in Stata, data management is far more than just a technical step. It is a fundamental component of effective research design that directly dictates the validity of our causal inferences. The visual on this slide metaphorically represents this journey: raw, disparate data points converging and being structured into a clean, organized table, ready for rigorous analysis. This entire guide has been put together by the Viet-Lod Economics Group. Let's dive in and understand how to achieve this crucial reproducibility.
The research lifecycle often fails at the cleaning stage. When we skip proper cleaning, our analysis can crash, or even worse, produce misleading results. It's a well-known reality in research that about 80% of a researcher's time is spent on cleaning and preparing data, with only 20% left for the actual analysis. This highlights the importance of mastering these skills. A critical issue in Stata is how it handles missing values. By default, a dot is treated as positive infinity. This means a command like age greater than 60 would incorrectly include individuals with missing ages, biasing the sample. Consider a real-world wage analysis. If missing income is coded as -99 and not properly converted to a system missing value, the average income calculated will be drastically lower than the true average. This leads to flawed conclusions and invalid policy recommendations. The first stage is acquisition, where we import data from various sources like Excel, CSV, or ODBC databases using commands like import Excel. Next is cleaning, where we inspect the data for anomalies and sanitize it. This involves handling missing values with mvdecode and ensuring variables have the correct type using dstring. Transformation is where we restructure the data to fit our analytical needs. This often involves reshaping from wide to long format or merging datasets. Finally, archiving involves documenting our data. We add labels, notes, and save the clean dataset, ensuring it's understandable for future use. This is where Stata's scripted nature shines compared to manual tools like Excel. Excel is ad hoc, manual, and hard to reproduce, while Stata is scripted, auditable, and fully reproducible. As the slide states, the transition from raw data to a tidy format is the primary objective.
This slide presents a decision matrix to help you select the appropriate data management method based on the structural problem you're facing. The first common problem is having data spread across multiple files. The solution here is to use the merge command, or the more modern frames functionality to combine them, typically using a one-to-one merge, or friend link. Another frequent issue is having the wrong unit of observation. For example, if you have yearly data in columns instead of rows, the reshape command is designed to solve this by converting data between wide and long formats. Finally, if your categorical variables are stored as text, they cannot be used in regressions or many analytical commands. Commands like encode or dstring are essential for converting these string variables into a numeric format that Stata can analyze. A best practice is to always plan your data linkage table before writing a single line of code. This foresight can save a lot of time and prevent errors. As a tip, always use Describe and Codebook first to understand the structure of your incoming files. This initial inspection is crucial for identifying potential problems early. Ultimately, success in all these transformations hinges on clearly defining your target unit of observation before you begin. This is the fundamental entity your analysis is about, such as a person, a firm, or a country year. All these methods aim to achieve one thing: a tidy dataset. Let's define what that means. The core principle of tidy data is that your dataset should be a rectangular matrix, which we can represent as n by k. In this structure, each row represents a single observation, and each column represents a single variable. This format is non-negotiable in Stata. Features like merged cells in Excel are the enemy of tidy data. This structure has a clear logic. Analytical operations, like calculating a mean, apply to columns, variables, while filtering conditions apply to rows, observations. Stata has a sophisticated system for missing values.
The key rule is that all missing values are considered logically larger than any valid number. This is why they are treated as positive infinity in logical conditions. There is a hierarchy. The standard system missing value, a simple dot, is the smallest. It's followed by extended missing values from dot A to dot Z. This allows you to encode why data is missing, adding valuable metadata directly into your dataset. For example, you could use dot A to signify refuse to answer and dot N for not applicable, as shown in the context box on the right. This allows for more granular analysis of missingness. The mvdecode command is used to convert common placeholder numbers, like -99 in older datasets, into the standard system missing value. This is a vital cleaning step. Conversely, mvencode can convert specific numeric codes, such as 98 or 99, into these extended missing values like .A or .B, preserving the reason for missingness while still treating them as missing. A crucial warning: to reliably isolate all missing values, including dot, .A, .B, etc., always use the condition if far greater than equal to dot in your Stata commands. This leverages Stata's hierarchy of missing values and ensures you catch everything. Beyond cleaning values, we often need to transform the very structure of our data. The most common structural transformation is reshaping, which we'll cover next. The reshape command is fundamental for panel data analysis. It typically converts data from a wide format, where each time period has its own column, to a long format, where there is one column for the value and another for the time period. The syntax is reshape long, stub, IID, JTime. Here, stub is the prefix for the variables you want to combine, like inc for inc90, inc91, etc. The I option specifies the entity identifier, which is the unique ID for each observation unit, like a person or a company. This variable tells Stata who the observation is about. The J option defines the new sub-observation variable, which is typically time. This variable tells Stata when the observation occurred. This long format is a mathematical requirement for running panel data regressions with XReg. If your data has variables ID, GDP 2000, GDP 2001, you would use reshape long GDP, IID, J year. This would create a new dataset with variables ID, year, and GDP, with 2 rows for each original ID. While reshape and merge are classic tools, modern Stata offers a more efficient way to work with multiple datasets, called frames. Introduced in Stata 16, frames allow you to hold multiple separate datasets in memory at the same time. This is a major architectural improvement. The primary benefit is that frames eliminate the need for the old preserve and restore workflow, which was cumbersome and could lead to errors. By keeping datasets separate and linking them virtually, frames reduce memory overhead. You don't need to create one massive merged file, which is especially useful for very large datasets. This approach also prevents data loss errors. Because the original datasets remain untouched, there's no risk of accidentally dropping observations or overwriting variables during a merge operation. Instead of merging a demographics dataset into your main financial dataset, you can load each into a separate frame. Then you can create a live link between them using frame link based on a common ID variable. This allows you to access variables from the demographics frame as if they were in the financial frame, but without altering either original dataset. Now that we understand the key concepts and tools, let's look at the essential syntax that ties everything together and ensures our work is reproducible. Every Stata command follows a basic anatomy. It starts with the command name, like summarize. This is followed by a var list, which specifies the variables the command should act upon, such as wage. You can add a condition using the if qualifier to apply the command to a subset of the data, for example, if gender equals 1. Finally, options modify the command's behavior. They come after a comma, like the detail option, which provides more detailed summary statistics. To ensure reproducibility, every Stata script should begin with a golden rule header. This includes setting the version to lock in the syntax, clear all to start with a clean slate, set more off to prevent pauses, and capture log close to manage log files. This is a best practice to always set the version to ensure code stability over time, guaranteeing your script runs the same way in 10 years as it does today. As a tip, use 3 slashes to break long lines of code for better readability. This slide presents our comprehensive toolkit for data management and cleaning, categorized into 4 essential areas. First, for inspection, we use commands like describe to see variable types and basic summaries, codebook for detailed variable information, inspect for quick data quality checks, and duplicates report to identify and report any repeated observations. Next, for cleaning, our toolkit includes distring to convert string variables to numeric, replace to change specific values, recode for transforming categorical variables, and mvdecode for consistently handling missing values. For construction, we have generate to create new variables, egen, extended generate, for more advanced functions and group-based statistics, and collapse to aggregate data into summary statistics. Finally, for managing metadata, we use label variable to assign descriptive labels to variables, label value to define what numeric codes represent for categorical variables, and notes to add important information or comments about the dataset. A crucial power user tip here is that egen, extended generate, is your most powerful tool for group statistics. For instance, to calculate the average wage within each county, you would use egen average wage equals mean wage by county. Also, a note regarding distring, it requires the force or ignore option if your data contains non-numeric characters that are not part of a valid number and should be removed or ignored during the conversion process. Our workflow begins by ingesting the persons dataset directly from the StataPress website using the use command. The clear option ensures we start with an empty memory. Immediately after loading, we inspect the data. The describe command gives us a summary of the dataset, including variable names and types. The list in 1.5 command allows us to view the first 5 rows of data to get a feel for the content and structure. The main goal at this stage is to prepare this person's data so it can be linked with an external dataset containing county-level statistics. This requires understanding its structure and identifying the key linking variable. When you run describe, you might notice that a variable you expect to be numeric, like ID code, is stored as a string, text. This is a critical observation that tells you a cleaning step with dstring will be necessary before you can merge or link on this variable. First, we create a new empty frame named counties with frame create counties. Next, while in the context of the new frame, we use the use command to load the counties dataset into it. The key step is friendlink m1 county, frame counties. This creates a many-to-one live link from our main persons frame to the counties frame, using the county variable as the key. The result is that the original persons dataset remains pristine and untouched. We have access to all the county-level data without a physical merge, which optimizes memory and prevents errors. First, we use mvdecode to handle any placeholder missing values, such as -99, converting them to Stata's system missing value. Next, we use reshape long to transform the data from wide format, e.g. inc90, inc91, to long format, creating a new year variable and a single income variable. Finally, we use xtset person ID year. This command declares the dataset structure as panel data, telling Stata that person ID is the individual identifier and year is the time variable. This is a prerequisite for running panel data models. After reshaping, we should always verify the transformation. Check that the new year variable was created and note that the total number of observations has increased, as each person now has multiple rows, one for each year. With the data prepared, we can run our analysis. Here, we use xtreg to perform a fixed effects panel regression of wage on education and age. The coefficient on education is 0.68. This means that for every 1 year increase in education, the hourly wage is predicted to increase by 0.68 units, holding age constant. The p-value for the education coefficient is 0.000. Since this is less than 0.05, we conclude that the effect of education on wages is statistically significant. While not shown in this abbreviated output, you would also check the R-squared value to understand how much of the variation in wages is explained by the model's variables. Based on this output, a policymaker could argue that investing in programs that increase the average years of schooling by 1 year could lead to a tangible increase in hourly wages for the population, as the effect is both positive and statistically significant. This 4-step process demonstrates a complete and reproducible workflow. Let's now summarize the key takeaways from our discussion. Reproducibility is not an afterthought. It is the standard.